All right, for this part, we will be looking at static equilibrium. So static equilibrium is something we already went over in Newtonian dynamics. Um, Here we're going to be looking at more complete version of static equilibrium because we have now two conditions that must be satisfied for the object to be in static equilibrium. Not only the net force should be zero, also the net torque should be zero, which means that object cannot have any linear net force or any rotational net force. Basically, it cannot move in a translational or basically net translational force or basically rotational, forces. So it cannot rotate, but it cannot move translationally. So for this one, then you can see, right, the applications are many, right? Buildings, dams, bridges, and any other structures, right? So they are basically have to be in a total static equilibrium. That means there have to be no rotation also involved. So this no net torque is now a requirement for those type of buildings. So for a rigid body in total equilibrium, there is no net torque about any point. That means our system cannot be rotating. So all the torques should be canceling, all the forces should be canceling. Okay, so that's the next few slides, the next few examples are going to be basically based on. In terms of, we are looking at the total static equilibrium problems where now we have two conditions satisfied. Condition one, the net force equals zero, which in a way can give us up to two equations, right? Net force in x direction equals zero, net force in a y direction equals zero. Then condition two, which is net torque equals zero. So you get basically one equation out of this because you get clockwise, counterclockwise can be combined in one equation. So in a way, you have now three equations. Equation one, net force in a x equals zero. Equation two, net force in a y equals zero. And equation three, net torque equals zero. We usually just keep it, two-dimensional here, plus the net torque. All right, so let's look at several examples. So here we have 120 centimeter wide sign hangs from a 5 kilogram, 200 centimeter long pole. A cable of negligible mass supports the end of the rod as shown. Um, what is the maximum mass of the sign if the maximum tension in the cable without breaking is 300 newtons? All right. So some of the important thing in this type of problems here is to identify your object of interest. That means which one is your object and what are the forces acting on this object. And our object is basically is this. So you have a pole, right? So 5 kilogram, 200 centimeter pole that has number of forces acting on it. So if I'm doing the free body diagram for this, for the pole, so there will be several, forces acting on it. But the idea here is all the forces should cancel each other, both in x direction and in the y direction. Also, there should be, no torque with respect to any of the axes. Okay, so let's first do the, free body diagram. So like, let's say, look at the forces. Well, one obvious one is the tension force, right? So here's the tension force. So input like this, here's a tension force, which is basically acting at this end of the pole. Well, there also, well, this pole has a mass and it has a length. So you can assume that all the mass of the pole concentrated at the center of mass, which is halfway, and the gravity acting on the pole at that position, which is basically somewhere over here, let's say. So there's this, the weight of the pole, right? Weight of the pole. Well, there's also a sign, yes, physics shop sign, which acting at sort of like two different positions. One is at the end, another one is right here. So then technically they are providing, two forces. So each one, since the sign connected to the pole by two tensions, so each tension from the sign is basically equal to half of its weight. So basically half of the weight of the sign, this one is half of the weight of the sign. You can see, right? Let me do it like this. Okay. And also the support point with the wall generally exerts two forces. One, there is a friction upward static friction. The other one is a normal force, like this. So you can see right there, quite a lot of forces acting on this pole. So then next step will be to the force table. So here we have tension, we have the static friction, normal force, weight of the pole. Then you can say that half of the weight of the sign, another half of the weight of the sign, because there are technically two different forces, right? Um, and that's it for now. Let's say here's the net force, and I know it has to be zero because the system is in static equilibrium. All right, now the tension is a two-dimensional force, so I can break it down into components. So then this is Tx and this is Ty. And to get, sort of like the angle, right? So I need to then basically, sorry, this is Ty, this is Tx. I made a mistake. So I can use the fact that I'm given that this is 250 centimeters. From here to there, this is 200 centimeters, right? I can then use the trigonometry to find that angle theta, between them. So because then I can use this theta and break it down, the x component as Tx. Tx is basically T cosine theta, and Ty is T sine of theta. And I can also see that Tx is pointing to the left, so it's negative. Ty is pointing up, so it's positive. Static friction has no x component acting in a positive y direction. Normal force is acting in a positive x direction, has no y component. Weight of the pole acting in a negative direction, negative y direction. Then half of the weight of the sign, both are basically negative, like that. So I get equation 1, which is net force in the x direction. So this is normal force minus T cosine theta equals 0. Equation 2, then in a y direction, so I have T sine theta plus the static friction minus weight of the pole minus 1/2 weight of the sign minus 1/2 weight of the sign, then this is equals to 0. Okay. Now, remember, my goal here is to find the maximum mass of the sign. That means if I would find the weight of the sign, I can then calculate this. From here, one thing I can see here is that unfortunately I cannot do that because I don't know what the static friction or the normal forces are. I don't know those values. That's because we're not given the coefficient of static friction, that we can have for that pole and, a wall interaction. So we're kind of stuck with these two equations. But then there's also a third equation, which is the net torque, which should equal to 0. And then for the net torque, here's basically what I have. So think like this. So this is the pole. So I have then 3 forces acting on it. So here's a tension. Here's the half of the weight of the sign right here, right? And here's the other 1/2 of the weight of the sign. Here's then weight of the pole. Then I have here's the normal force, and here's the static friction. So those are basically the forces acting. Okay. Now, in order now for me to get the net torque, well, first I need to know, okay, what is the axis of rotation? What is the pivot point? And here's the interesting part. Because your system is in static equilibrium, there is no pivot point. It's not rotating. So there is no true pivot point. There's no true axis of rotation. So what do? Well, we are free to choose any point we want to be our axis of rotation. That means I can take this point over here. I can take that point. I can take this point, or I can take that point, right? Any of those points are fine. But obviously, one of the things you want to do here is choose a point that is the most convenient. So for example, like let's say if I'm using my equation, so this will be torque, let's say, remember it's a net, the net torque is a vectors, right? So then it's torque due to the static friction. plus torque due to the normal force, plus torque due to the weight of the pole, plus torque due to the tension, then plus torque due to the first 1/2 weight of the sine, plus torque due to the second 1/2 of the weight of the sine, then equals to 0. Okay, so I have, 6 different, torques acting on it. But what I can do here is I can choose one point to be axis of rotation that can eliminate any force that's going through that axis of rotation. Remember, right? Any force going through the pivot point is 0. So think like this. If I choose this left end to be the axis of rotation or my pivot point, then it eliminates static friction and a normal force, and they don't exert any torque. And that's what I want, because I don't know any information about them. And I don't need to if I take that point to be my axis of rotation. So then my torque equation will be this. Net torque is equals to torque due to the weight of the pole plus torque due to the tension plus torque due to the weight of the sine, right? So 1/2 weight of the sine plus torque due to the other 1/2 weight of the sine. Again, I'm not combining them because they give me different torques with respect to the left end, right? Because their R's is different, right? So this first 1/2 weight of the sine is closer than the second one. So they give me different torques. So that's why I'm not combining them. So then this is equals to 0. And that's what I'm going to do right now. Taking that left end to be my axis of pivot point or axis of rotation, I'm going to first write in terms of weight of the pole. Well, weight of the pole is basically the torque, right? To the weight of the pole is the force magnitude, which is mass of the pole times g, then times its distance, which is half the length. So it's 0.1 meters or 1 meters actually, right? Because it's 100 centimeters. And I can see, right, if I'm doing the R and weight of the pole or half of the weight of this, pole of the sines and things like that, all perpendicular to the radial line. So technically then sine of angles basically is sine of the 90 degrees 1 for them. That means this is this guy over here. So it's sine of 90 degrees. And I can see that weight of the pole going to give me sort of like, let's say, a negative, right? Clockwise, a rotation. So this guy here is negative. So then plus torque due to the tension. So the torque due to the tension here is the only one that actually giving me positive. And I can find using, again, tangent of theta equals 250 over 200. Then I can find this angle theta. So using that, I can get the theta equals to 51.3 degrees. Okay. And then say, all right, so for the torque of the tension is the tension magnitude. So basically, let me do it like this first. So it's tension times the distance, which is basically, 2 meters, and then times sine of 50, let's say sine of theta right now. Let me put it like that. So, and it's positive because it's going to give me counterclockwise rotation. Then minus, so let's go to this guy. The first, weight, half of the weight of the sine. So it's minus because it's going to give me clockwise rotation. So minus 1/2 mass of the sine times g. So this is its magnitude. Then the distance, and I can see it's given that, it's 80 centimeters from the left end, right? So it's basically 0.8 meters. Then sine of 90. Then minus, then the second weight of the sine. So same way, 1/2 mass of the sine times 9.8 times distance, and the distance here is 2 meters. And again, it's sine of 90, so I can just ignore that. So that all equals to 0. Right, so and you can see, right, all I have right now is that if I replace this mass of the pole with 5 kilograms and this G with the 9.8 and this tension here with the 300 newtons, the only thing I don't have is the mass of the sine. Everything else is basically given to me. So then I can solve for the mass of the sine, and it equals to roughly 31 kilograms. All right. That means mass of the sign is roughly 31 kilogram. And I use the net torque by choosing the pivot point to be where the pole connects with the wall, and it eliminates those static friction and a normal force. And then I have just only four forces applying torque, and I know basically everything that I need right now to just solve for the um, mass of the sign. Okay, so, and this is how you basically solve this type of problems. You first do your free body diagram, then you force table, then set up the equation for the net force in X and Y, right? So those two equations. And if you can solve whatever you want from those equations, fine. If not, then include the third equation, which is for the net torque. Sometimes maybe starting with the net torque equation is easier. You might be able to just solve for the unknown directly from there. All right, here's another example. So this is also kind of like a typical example where we have a ladder leaning on a wall, right? And basically the friction from the wall and from the floor prevents it from, sliding. So it's in a static equilibrium. All right, so let's look at it. So you have a 3-meter long ladder leans against a frictionless wall. The coefficient of static friction between the ladder and the floor is 0.4. What is the minimum angle the ladder can make with the floor without slipping? Okay, so basically we need to pretty much find this, angle, that it makes um, with the floor without slipping. All right, so let me do my own free body diagram so I can kind of like explain as we go. All right, so let's say here's the ladder like this. All right, so it makes two points of contact, right? So one is right here with the wall, and another one right there. So for example, there is this normal force. So there are two normal forces, one from the floor, one from the wall. So okay, so here's one, let's call this N2, and here's another one, let's call this N1. And there's also two frictions, sorry, one friction, because it's a frictionless wall. If the wall is not frictionless, then there would have been another force, friction force from the wall. All right, so think like this. So if the ladder would be, let's say, slipping, right, it would be moving, let's say, to the right. So then the floor prevents it from that. So there's a friction force from the floor in this direction. Also, if let's say the wall was not frictionless, that there would have been a friction force like this from the wall. But we don't have this in this particular example. But you might see an example where there is a friction on a wall, right? And then that friction will be like upward, because otherwise the ladder will be let's say slipping downward, right? So it would have been preventing. Okay, so those are the three, forces from those two contact points. But there's also another force, which is gravity acting on the ladder at the center of mass. You can see, right? So, and that's exactly halfway. So then we have this, let's say F of G, right? Like this, right? So now those are the forces acting basically on our ladder, and the ladder obviously is the object of interest. So net force should be 0. So then we can write down in terms of our forces, force table, X component, Y component. So I have, all right, so let's say gravitational force, normal force 1, normal force 2, and then the static friction. Again, the net force should be 0, 0. You can see then the gravitational force is straight down. Normal force 1 is straight up. The normal force 2 is in a positive X direction, and static friction is a negative X direction. So you basically get something like this. All right, so equation 1 is then N2 minus F of S equals 0, and equation 2, N1 minus F of G equals 0. So basically we have this. That means in a way normal force 2 is equal to the static friction, And normal force 1 is equals to then, let's say mg, right? The weight. Remember, our goal is to find the angle that it will make. That means the ladder will make with the floor. That means we want to find what is this angle theta. Okay. Now, looking at these equations, right, I can't really solve for the angle theta because I don't have any information from here whether there's theta. I can even simplify with this a little bit because f of s equals then mu s times normal force 1, and this is equals to then mu s times mg. So this is kind of, as far as I can go from here. But then next I can use the equation 3, which is the net torque. Okay. And for this one, then I can choose any point to be my pivot point. Then I can then try to find some kind of information about the angle theta. Okay. So again, any point could be a good point for the pivot, but ideally you want to choose a point that eliminates as many forces as you can have. So your equation of the torque is just much simpler. So for example, if I choose this point right here to be my pivot point, then the torque due to the normal force 1 and due to the static friction, they're disappeared, they're gone. All right. That means what I can do from here is this. Our net torque now is going to be in terms of torque due to the normal force 2. And it's going to be negative because it's going to give us, with respect to that, sort of like a clockwise. And then plus torque due to the gravitational force, which kind of going to give us clockwise, counterclockwise. So then this is equals to 0. Then here what I'm going to use is that lever arm method. So that means if I kind of extend this normal force 2, right? So see, if I extend, then the direct closest distance from the pivot point to there, let's call this D2, or sorry, let's call this D1. Well, it is D2, so according to that. So let's call this D2. And then same thing I do for the gravitational force, go like this, and then this distance. So this distance I'm going to call this D1. Okay. That means it's negative N2 times D2, then plus, then mg times D1. And this is equals to 0. Then I can look at it in terms of, okay, so what is, let's say then D1? And what is, let's say, D2? Okay, so from here, again, using, let me kind of make this a little bit cleaner. For example, this is what we get. See, this is my theta. Okay, this is my theta. And my theta is for, let's say, this triangle. Let me make it in a, basically for this triangle, for the gravitational force, D1 is the adjacent, right? Then this distance, which is half of the L, is then basically becomes the hypotenuse. Okay, so then I can rearrange those and have a D1, which is the the x component or adjacent side. Remember, in terms of, let's say, cosine theta, right? Because cosine theta is adjacent over hypotenuse. So D1, which is the adjacent, will be hypotenuse times cosine theta. That means this term basically becomes, so mg times 1/2 times the length times cosine theta. All right, minus, now let's look at this term. What is D2? Well, this theta is same as that theta, right? And in this case, then D2 basically becomes the opposite to that, let's say, to that angle. So then that basically becomes in terms of where the hypotenuse is the entire length of the ladder L, and then this becomes just basically N2 L sine of theta equals 0. All right, so that's basically what I end up with. And then I can say, all right, so then mg 1/2 L cosine theta equals N2L sine of theta, right? So I end up with that. And from here, I can see that I can pretty much even cancel the L's. I don't need that. And then I'm going to divide both sides by basically cosine theta. So if I do that, this will go away. And on the right side, if I divide both sides by N2 as well, this will cancel out. What I'm doing here is I'm eliminating everything on the right side. So I have sine over cosine, which is nothing but the tangent of theta. And what I have surviving on the left side is basically mg times 1/2 over n2. Okay, so let's do that. So it's mg times 1/2 over n2. But going back and remembering that n2 is mu s mg, I can come back and rewrite n2 as mu s mg, which means that mg and mg can cancel out completely. And all I have here is basically 1 over 0.5. So, sorry, it's 0.5 at the top. So it's 0.5 over mu s, which is then 0.4. That means my tangent of theta is 0.5 over 0.4, which is 1.25. So tangent of theta equals 1.25. So for theta from that, we get 51 degrees. That means this is basically the minimum, right? This minimum angle it can have in order for the ladder to not start slipping. So that's the minimum angle that we can have, which is theta minimum is 51 degrees. All right. The next we're going to look at what we call a rolling motion. So I mentioned that earlier that if you have a sphere or a disc and you can have kind of like, let's say, two types of motion. You can have first, the disc can be moving, like I said, sliding, right, without rotating, or you can have the disc just rotating without moving, or it can have it moving and rotating, which becomes basically the rolling motion. That means, for example, if this is your disc, you can have two things. You can look at center of mass, which will be then moving with some velocity. And remember, center of mass, even if the disc is rotating, center of mass is the only point that is not rotating. So if this disk is moving to the right, it's same as for the center of mass, it's just basically going in a straight line. But if I choose a point on the edge, if it's rolling, then it's kind of going like this, kind of like a helical, motion. So then we can always assume that V center of mass equals R radius times omega. And then we can have sort of like, let's say, a motion of a disk that can be combined in terms of translational and rotational. And we're going to see that in the next few slides. So you can see, right, taking the time derivative of position of a particle I in a rolling object. So you can see, right, VI is equals to V center of mass plus VI, which is relative velocity with respect to this, inertial reference frame. The velocity of the particle is the velocity of the center of mass of the whole object plus the velocity of particle I, which is some random particle, right, in the disk, relative to the center of mass. That means, when it's rolling, you cannot just look at the center of mass, or you cannot just look at, particle on the rim. You have to look at all of those things combined together. So that's why we have sort of like, let's say, we have to look at combination motion, which is basically we call it rolling. So think like this. Combination is combining translational motion, where imagine you have a disk that is not rotating, basically it's sliding, right? So let's say in this first image, it is sliding to the right. That means if it's sliding, so the top, center, and the bottom, all of them moving with the same speed to the right. Again, because it is sliding to the right. Okay. So, but you can have, or just purely rotation, where it is not sliding, you just, fix it to one position, but it's rotating, which means that the top has a, and let's say rotating clockwise. So the top basically rotating with r omega clockwise, and the bottom, right, moving then negative r omega, because again it's clockwise, but bottom basically has a velocity to the left. But if it's rotating, center of mass is not moving at all, so it has no velocity. But rolling is basically combining those two together, which means I combine the tops together, and then now the top is 2 times r omega, becomes, because both v center of mass, which is r omega, and other r omega, both of them in the same direction, you're adding them together. That means top is moving twice as fast. Center, if you adding them together, translational is v center of mass, rotational is 0. So then you get v center of mass. The bottom though, you can see if you're combining translation and translational is velocity to the right, rotational velocity to the left. So you get 0 velocity, which is velocity 0 at the bottom. And that's the important thing. That means if object is rolling, the bottom of the rolling object is instantaneously at rest. That's why we used to talk about it. Remember Newton's third law? When you're walking or when you're driving a car, right? The tire is the propelling you forward, but we can say the tire or your bottom of your shoes, right, is instantaneously at rest. Because when you're combining translational and rotational motion, velocity at the bottom equals to 0. So that's kind of like one of the things we can think of, like in terms of if it's a rolling, you have to do that. Also, what do you need for the rolling object? Well, you need friction, right? Because if there's no friction, it will be just sliding. So you need, for the rolling, you need friction. So the friction will allow you to actually roll. Which means then, if the object is rolling, there are 2 types of kinetic energy that we have to consider. One kinetic energy is rotational. One kinetic energy is translational of the center of mass. So kinetic energy of the rolling object is 1/2 I center of mass omega square, then plus 1/2 mv center of mass square. So which means that, for example, if you have an object at the top of the incline, and it's not like, let's say, a box that is sliding, like let's say something that can roll. So we used to say, okay, so this is my point A, then this is, let's say, point B, and it goes from point A to point B, and what will be the velocity at the bottom? So before we would say, if there is no friction, an object was sliding, then kinetic energy at A plus potential energy at A equals kinetic energy at B plus potential energy at B. I would say then, taking the object starting from rest, this is 0, and then position of B is 0, so there is no potential energy there. So what I could say then mgh, right? H is being the height, is equals to then 1/2 mv squared. Now, this would have been true if the object was sliding and there was no friction. But if we have an object there is a rolling, that means now I have to add 1/2 I omega squared. And in order for object to roll, what do I need? I need friction. So then how does it work? If I have a friction, can the energy be conserved? Yes, if the object is rolling. Because remember, what can dissipate energy is the kinetic friction. But remember, at the bottom of the object, right, the rolling object, it's a static friction. And that means energy can be conserved. So you can still have this equation, which is conservation of energy. If it's a rolling object, as long as basically it's a shape that can allow it to roll without slipping, right? And it can go from point A to point B, and you can use this to solve for the velocity. One thing we usually do here is we replace this omega, for example, with this equation. Remember, V equals R times omega. We replace omega with V over R. And also I, if it's a disk, is 1/2 mr squared. And then we replace it and then solve for the velocity, linear velocity. It means what is the linear speed at the bottom? Then you can replace, this omega with V over R, moment of inertia with 1/2 mr squared, and then you have just one V. We can factor out and then just solve for that speed. Okay. So one-dimensional motion uses scalar velocity V and the force F. More general understanding of motion requires vector V and vector force. So similarly, a more general description of rotational motion requires us to replace the scalars omega and torque with the vector quantities, omega of the torque. So now, because we've been kind of talking about angular velocity clockwise and angular velocity counterclockwise, or the torque clockwise, torque counterclockwise, well, that's not quite accurate, because when you're considering, torque or the angular velocity or the angular acceleration, they're not really clockwise or counterclockwise. So we're going to see in this next few slides, there's a little more complicated than just clockwise and counterclockwise, which are a little more simplified picture of that. But it is still accurate enough for us to be able to get the solution correct. In order for us truly get the direction of the angular velocity, for example, we have to use what we call a right-hand rule. Okay. So the right-hand rule goes like this. So if you have a disk that is rotating, right? So what you would do here is you use your right hand, and if you curl your fingers in the direction of your rotation, so let's say in this case counterclockwise, see your thumb will be then pointing in the direction of the velocity, angular velocity as a vector. That means angular velocity technically is perpendicular to the plane of rotation always. So same way you can see, right? If the disk was rotating clockwise, then you would rotate your fingers in the direction of the clockwise. So then your thumb will be then going down, which would have been in basically, so let's say if there's a disk rotating clockwise, then your thumb would have been, pointing down. I don't know, something like this, right? Because your fingers will be then going, let's say, counterclockwise, or maybe like, let's say, would have been more accurate if I kind of do it like this. So those are your hands, right? So if I'm doing that my fingers rotating counterclockwise, sorry, my fingers rotating clockwise, my thumb is pointing down, which means then in this case, angular velocity would have been down. So this is counterclockwise and angular velocity is up. This is clockwise and angular velocity is down. And this is basically the true correct direction of the angular velocity. So we have to use this right-hand rule to determine, that true direction of the angular velocity. Now, if this disk, for example, is rotating counterclockwise, and let's say this is omega, and it starts spinning faster, that means alpha is also in the same direction. Okay, alpha is also in the same direction, which is, upward. But let's say if this is a disk counterclockwise and starts slowing down, then alpha is in opposite direction. That's why opposite direction, you start slowing down. That means alpha also always perpendicular to the plane of the rotation. And if it's in the same direction as omega, as a vector, right, then you speed up. If it's in the same opposite direction of omega, then you basically slow down. Which means then this type of arrangement requires us to use a cross product, which is sometimes also known as a vector product. So that means you have two vectors, right? So and when you multiply those two vectors together, then you get basically a vector quantity this time. So that's why, for example, if we need to understand, for example, angular momentum, which we're going to see in the next few slides, right? We need this cross product. That product was something we used before for the work done, if you remember, force times delta R. So for work done, it was F dot delta R. So which has basically two equations. Remember, it was FR sine of cosine of theta. So, and this was a dot product. That means, we do magnitude of the force times magnitude of the position equals cosine of theta. And the answer was a scalar quantity. And even if it was basically the dot product of, let's say, components, we would have just get, again, a scalar quantity. Now, the cross product is a little more complicated. Sometimes can be a whole lot complicated if it's three-dimensional. But one thing we have is let's say if you have two vectors, so let's say A cross B, if you know the magnitude of each vector and the direction between them, then it's simple enough. It's AB sine of theta or sine of alpha. Let's take alpha as the angle between them. So for example, let's say you have two vectors, so you can see, right, A and B. If you then do A cross B, well, A cross B means that, it's A, B sine of angle between them. If A and B are parallel, alpha is 0, so sine of 0 gives you 0, which is a cross product between two parallel vectors, basically gives you 0. Next, we have a cross product between two vectors that have an angle 30 degrees with respect to one another. In that case, so the A cross B is not 0 anymore, so you just basically do AB sine of 30, and then you can calculate this. And if you have two vectors that are perpendicular to one another, where alpha is equals 90 degrees, A cross B is just an A times B, which means you get the maximum amount of, let's say a resultant, and AB just a product of the magnitudes, because sine of 90 is equals to 1. That means it is easy if you have the magnitude of the vectors and the direction between them. But it's not necessarily that easy when you don't have them, when, let's say, they're given in terms of their components, right? So I'm going to give you an example in terms of what to do if they are given in terms of their components. All right. So let's say you have two vectors, A cross B. And what you're given here is this. A given in terms of AX I hat plus AY J hat, right? And let's say plus AZ K hat. That means it's a three-dimensional vector. Then cross, and then you have bx I hat plus by j hat plus bz k hat. That means you have three-dimensional vector for each one, and you're doing the cross product of them. Right, so the easiest way to go around and finding this is to do the 3x3 matrix. So think like this. What we'll do here is this. So I'll make a matrix like this. So then I hat, j hat, k hat. Then this is ax, ay, az. This is bx, by, bz. Okay. So we're going to start with this, and then we're going to do basically break this down into three 2x2 determinants. Okay. Because one thing we're going to do here is we're going to do one determinant for the I hat. For that means, I'm going to use anything that, so let's say you take the I hat, and then you do horizontal and vertical lines, and then basically eliminating everything that, then should not be going into this determinant. Then this determinant for an I hat will be everything that basically survives if you kind of go vertical and horizontal like this. That means it's going to be then AY, AZ, BY, BZ. Okay, then minus is minus part of the equation. Then if you come back here, so let's say if I do this, right? So then, I have, for example, now I have for the J hat, again, same thing, right? So I eliminate like this, and only the AX, AZ, BX, and BZ go into this 2x2. This is for the J hat. Then plus, so basically the same thing I do for the K hat, which is eliminating like this. And then the rest of them then go into this. So then this is AX, AY, BX, BY, K hat equals to. And then for here, hopefully you guys remember how to do 2x2 determinants. So product of AY, BZ, then minus product of AZ, BY. So that's my I hat component of the resultant, which is a resultant is some vector C, let's say. Then minus, same thing I do for the second one. So the AX, BZ, right? So the product of those minus the product of these two. Then AZ, BX, J hat. Then plus, then AX, BY minus AY, BX, and that's my K hat. That means this is what the CX component is. This is for the CY, and this is for the CZ. That means the X, Y, Z component of my resultant vector C. Right, so this is, one of the ways we can do. So that means if you have a little bit complicated, A, B vectors in terms of their components and things like that, this is the one of the ways you can do. Another way, for example, is to remember one thing. The unit vectors, if you're doing I hat cross I hat, for example, so this is the magnitude of each one, remember is 1, right? So magnitude of 1 times magnitude of the second one, which is, it's a unit vector, so their magnitude is 1, then times sine of angle between them. Well, if it's I hat and I hat, they are parallel to one another, so it's sine of 0, so you get 0. That means two I hat vectors or two J hat vectors, two K hat vectors. If you do cross product, you're going to get 0 because, as I mentioned earlier, right? Cross product of two parallel vectors are always 0. But for example, then you have I hat cross J hat. What do we get here? Well, for this one, it's 1 times 1, then sine of 90 degrees. Well, that means this is just basically 1, because 1 times sine of 90 is 1, so you get pretty much 1. Okay, so how about if you do I hat cross negative J hat, for example? Okay, well, remember, that means this is I hat, and this is J hat, negative J hat, right? So then you can do 1 times 1 sorry, I need to go back here for a second. It's 1 times 1 sine of 90, which is equals to 1. That's correct. But also we have to do this. Well, the cross product has to give us a vector. That means you have to also get a direction. So how do we get a direction for this one? Well, think like this. So you have this, right? You have I hat, J hat, and K hat. So use your right hand, for example, right? Use your right hand and have your fingers first in the direction of the I hat vectors. So let's say your fingers direction of the I hat vector, because that's your first vector. And then try to curl your fingers in the direction of the J hat vector. And then one thing you will see, your thumb will be pointing out toward you, which is direction of the K hat. That means this will be 1 K hat. That means you have a magnitude and the direction for this one. That means you're going to always get a direction out of that as well. Okay. So for example, here we have I hat cross negative J hat. All right. So what we get here is this. So you can see, right, they are perpendicular to one another. So that means there's a cross product. So in this time, you have your fingers in the direction of the, I hat again, but you need to curl in the direction of the J hat, negative J hat, which is down. And if you do that, then your thumb will be pointing then into the page. If you do that, which means then this is negative K hat. Okay. So again, there's a table in the book, right? You guys can look at it in terms of that, but it's, you can also learn that using the right hand rule, by doing that. So there are several right hand rules, and I have a slide on that, so you guys can see that. So let's go back to the slides. Okay. So here I have, several ways we can do the, a right hand rule. Here's pretty much what I'm using. See, let's say, for example, your fingers first in the direction of the first vector, A. Well, I mean, assuming that looks like a finger, like something like this, right? Like that. And then you curl in the direction of the second vector, which is B, right? So you curl in the direction of the second vector, which is B, and your thumb gives you the cross product direction. Or you can use this version, which I don't use, but you can use it. For example, your thumb is the vector A, first vector. Then your index finger in the direction of the vector B, which is the second vector. Then your middle finger will give you the direction of the resultant. Okay, so A cross B, which is, first vector, second vector, and then this is the resultant, the direction of the resultant. Okay, so for example, if I'm doing the, let's say, coordinate system like this, you can see, right, if vector A is along the x-axis, vector B along the negative z-axis, then resultant will give me the positive y-axis. That means I hat cross negative k hat, for example, gives me plus j hat. I can kind of do it in terms of this. Also, b cross a is not equals to a cross b. B cross a equals negative a cross b. That means, for example, if you switch going from b as the first vector and a as the second vector, the direction actually will switch. You can try that on your own and we'll see that will be, true. So the reason we're learning about the cross product, because torque then is technically a cross product between displacement vector and a force. So you can see, right? So let's say this is, you're using a wrench, right? So let's say you apply force and you apply force some distance r from the, pivot point. So then technically that's a vector, r vector, and this is the force vector. And then you're doing the product of two vectors to get a vector, which means we have to use a cross product. Again, this is equals to RF sine of phi. For example, if you are given those values, right, R and F and sine of phi, and then you can use then your right hand to find the direction of the torque. So in this case, right, if you're doing the direction of the torque, you can say then here your fingers in the direction of the R, and then you have to curl in the direction of the force. In this case, your thumb will be pointing out of the page. So you'll be pointing out of the page. So let's say this is your hand. I have a hard time drawing I guess a right hand. So then, you're gonna get something like this, where your thumb is basically pointing out of the page. So this is, again, the net, this is the torque equation. This is the equation if you have their, magnitudes. But also, you have to understand, if you have them in terms of their components, you can also use the method that I showed you. So let's look at it over here, how we can find that. So it says, suppose the vector r is in the xz plane and is given by r equals 1.2 meter I hat plus 1.2 meter k hat. Calculate the torque, a vector torque, if F is equals to 150 Newton I hat. All right, so in terms of then what I had, let's say that 2x2 matrix, right? 3x3, right? So in a way you can use that. So R cross F equals, so then I have, let's say, I hat, J hat, K hat, and then here I have then 1.2, 0, and 1.2. And then for the force, I have 150, 0, 0. Okay. So remember, so then what we did, basically we did, um, let's say if I do this and I eliminate them like this. So for the I hat, I have 0, 1.2, 0, 0, then minus, then for the J hat, I end up with 1.2, 1.2, 150, 0, J hat, then plus, this is for the K hat. I eliminate those and then I have a 1.2, 0, 150, 0. Okay, so that's basically then what I get out of this, and this is equals to, so then if I look at the first one, it will be 1.2 times 0 minus 0 times 0 I hat, which means this whole thing is 0. Then minus, here I have then 1.2 times 0, right? Remember, like this. Then minus 1.2 times 150. All right, so the J hat, that means, this goes to 0, but not the other one. Then plus, and then here you can see, right, again, 1.2 times 0 minus 0 times 150 K hat. This also goes to 0 completely. That means that our answer here is negative just 1.2 times 150 J hat, right? That means that's the only thing now surviving for us. And that's, what we have to use in terms of to do the calculation. Okay. So if I do this, 1.2 times 150 should give me negative 180 newtons times meters, right? Because this is in meters, this is in newtons, J hat. Okay. So then this is the answer. That means it's 180 newtons in a negative j hat direction, or negative y direction, basically. That's one of the ways we can do. All right. So the one of the last things we have in this chapter, and you can see, right, this is a rather really lengthy chapter, is that we can also find angular momentum. So we have found the rotational equivalent for everything. So rotational equivalent for displacement is angular displacement, right? Theta. Then for the velocity is omega. For the acceleration is alpha. For the force is torque, right? For the mass is moment of inertia. Then we have also energy, right? There's a translational kinetic energy, there's rotational kinetic energy. But there was also momentum, linear momentum. Well, now we also can talk about the angular momentum. So let's say we have a particle with mass m moving to the right with some velocity, so we can calculate its linear momentum. P equals m times v. But also, if we have some kind of, let's say reference point, then with respect to that reference point, we can also calculate the angular momentum, which requires for us to know the linear momentum of the particle and how far away that particle is rotating relative to some reference point. That means right now it has a distance r from that, and more or less you can see, right, if this is the direction of the momentum, it's kind of a sensation of kind of like giving us a rotation like that. So then what we can calculate here is angular momentum, which is defined as the cross product between that displacement r vector and the momentum as vector. So that's why it's a cross product. Okay, that means L as a vector is equals to r cross p. If I have r and if I have the p, then angle between them, I can use this. I guess we can use beta because it's giving us base beta. So we can calculate this in terms of the angular momentum from the distance, momentum, and angle between them. Also remembering that momentum is mass times velocity, then we can kind of like put it in terms of this. But this is just a magnitude. We also need a direction, and we have to use the right hand rule then. See, the r is our second vector, p is our, so r is our first vector, p is our second vector, using the right hand rule, right, where these are your fingers, right, and then you have to curl in the direction of the p, then your thumb will be basically pointing up, which then will be, upward, perpendicular to both of those vectors. That's how the cross product is. Cross product is always perpendicular to the both vectors that we have. Okay, that means this is the cross product between distance or the displacement vector and momentum. And this is the angular momentum for a particle. That means you have a particle with mass m with some velocity moving, and you can calculate this angular momentum relative to some, reference point. And the angular momentum can technically change if I change my reference position. For example, if I'm doing with respect to, let's say, this point, then my r then becomes this one over here. Okay, so then my angular momentum can change. Okay, but as long as there's a a beta right between them, I can still calculate that. That's a non-zero beta. I can calculate angular momentum. But for example, if I take my reference position right here, so that's my reference position right there, and this is, let's say this is my r, then actually I can see that there is no angular momentum. Why? Because vector r, sorry, vector r and vector p are parallel to one another. Again, I'm not using this. Let's say I'm using this one over here. They're parallel, and cross product between two parallel will give you it gives you zero, right? Which means think like this. If this is my reference position, if the particle is moving like this, there's no sensation of rotation, right? It's just going in a straight line away from it. See, with respect to this particular position, it is, can possibly kind of go around like that. See, if I'm doing, let's say, this circle, see, it's like tangent to that circle. But if this is my, let's say reference position, then there is no, let's say, like let's say some kind of rotational motion, right? It's going away from, directly going away from that, a point O. So there is no angular momentum with respect to that point. That means angular momentum for a particle can change depending on, let's say axis of rotation that you can choose. All right, so that means now we have this definition, right? So why is this with this definition L equals R cross P? So one of the things we have here is this. So angular momentum, again, it's think like this. It's a momentum of a particle relative to some reference position, okay? So, or the pivot point or the axis of rotation and things like that. And one of the things we have here is this. So if you take the time derivative of L and use the definition of the torque vector, so we can find that dl dt is equals to the net torque. That means I have d dt, right, of this r cross p, which then can give us basically, so from here, if I do that derivative, what I will get here is this, dr dt cross p, then plus p cross, sorry, r cross dp dt. So we get this. Okay. So then from here, one of the things we will see is then this first term going to go to zero. This first term goes to zero. Second term, because remember, the reason it goes to zero because the derivative of position with respect to time is then velocity. And the momentum is mass times velocity. So you're doing cross product of the velocity and velocity. So you're going to get zero. The second term becomes an r cross dp dt. And if you remember, dp dt was nothing but the net force, right? So net force, which means this becomes r cross f. And if I'm doing r cross f, we just learned that r cross f is then the torque. So that means change, the root of the angular momentum with respect to time is equal to the net torque. So, which means that very similar to this equation where the derivative of the linear momentum as a function of time was equal to the net force. Okay, so this is kind of equivalent, equations where the change in momentum requires some kind of force and change in angular momentum requires some kind of torque. And the torque then has to be some kind of external torque. So some kind of external torque that acting on the object to change its, angular momentum. Okay, that means angular momentum, remember, can be changed if you change the axis of rotation, right, or change your velocity direction and or change your distance and things like that. So that was for let's say for the particle. But one of the important things here we can do here also look at the angular momentum of a rigid object, or like let's say a disk. Well, it's not a single particle, right? It's a collection of particles, right? So there are like billions and trillions of particles within that disk. Now, that means one of the things we can do here is if I'm looking at the angular momentum, so this will be then more or less. So remember, it's like r times p, right? For this will be like for the first one, then plus let's say sine of beta this for the first one, then rp sine of beta for the third one, and so on and so forth. So we can kind of like add them all together. And one of the things we're going to be doing here is if I start adding all together and things like that. So think like this here, L, right? For example, this is R times P, and let's say beta is 1, so beta is 90, so sine of beta is 1. So let's say, just look at it in terms of R times P. So this is then R times M times V. So then this is R times M. What I'm going to do, I'm going to replace V with omega. Remember, because if it's a rigid object, I would rather work with omega rather than V. I'm using this R V equals R times omega, then I have R times omega for the V. That means the angular momentum now is equals to R squared times M times omega. So R squared times M times omega. All right, so now from here we can remember one thing. Sorry. R squared times M is nothing but the moment of inertia. Remember, it's mr squared. And if I'm then summing them up, right, all the mr squares for all those particles, individual angular momentums added together, then I can then just write down this in terms of moment of inertia times omega. And that's what we have. Angular momentum of a rigid object is then moment of inertia of the system, let's say, times angular momentum of the system. See, this is for the particle, but moment of inertia for like a disk like that is 1/2 times total mass times the radius square. Okay, so this is then will be for the let's say a disk. Okay, and then what I have is then the angular momentum is moment of inertia times angular velocity, and the angular velocity, remember, is the same constant for all the particles, so it is much more convenient equation to use. So that means uh, net torque can change the angular momentum of this particle. Okay, so let's say now in terms of you can think like, let's say this is kind of very similar to the linear momentum, right? So if you what changes linear momentum is net force. So let's say if this disk was initially at rest, then angular momentum, which is I times omega, would also be zero if the initial omega is zero. That means let's say you have a disk just sitting there, its initial angular momentum is zero. What do we do to change the angular momentum? Well, give it a torque. If I give it a torque, it's going to start rotating. Then final angular momentum is I times omega final, and omega final is no longer zero. So now I have a, you know, angular momentum. That means change in angular momentum as a function of time, you can see, is what we have this net torque. All right, so summarizing everything. So we have a rotational kinetic energy, there's a translational kinetic energy, there's a angular momentum, and there's a linear momentum in terms of center of mass. What changes angular momentum is the net torque. What changes linear momentum is the net force. The angular momentum of a system can also be conserved if there is no net torque, just like linear momentum of the system is conserved if there is no net force. So for example, if you have a disk, as I mentioned, right, with some radius r, right, with mass m. So let's look at the angular momentum of this right now. So it's moment of inertia times angular velocity. Well, it's going to be zero if it is sitting at rest. Okay, just like let's say you have an object with mass m with no initial velocity, its momentum initial is just m times v initial equals zero. What do I do to change the angular momentum? Or same way, what did I do to change the linear momentum? We applied force, and this force was then reason that momentum was changed. Same thing, right? So let's say if there's a string wrapped around, so then I pull it down, so there's a tension force. That means there's a torque, right, acting at this distance r from the axis of rotation. Then this torque is equals to dl dt. It's going to change it, right? Because it's going to start rotating and the angular momentum will change, just like this will change. But on some cases, right, when there's a, let's say, no external torque, and this is a, this tension, right, is external, so it gives me external torque. If the external torque is zero, then you can actually have conservation of angular momentum, just like we had a conservation of linear momentum when two objects were colliding and the forces between them was basically internal forces. Same thing I can have here. An isolated system that experiences no net torque can conserve angular momentum. So the law of conservation of angular momentum, the angular momentum L of an isolated system is conserved. The final angular momentum is equal to the initial angular momentum, and both the magnitude and the direction will be unchanged. So very similar to the conservation of linear momentum. And probably one of the best examples here is when you are looking at the ice skater who is spinning. So the external torques can be small or zero because she's on ice, right? And we can then observe this conservation of a linear momentum. So linear momentum initial is the initial moment of inertia times initial angular velocity. And one of the things we can have here is this. So let's say she first was spinning with her arms extended like this. So like, let's say she was spinning like that. And this will be the angular momentum of her when she has this shape. So what we have here, if you remember, the moment of inertia depends on the shape of the object and how the mass is distributed. The mass, the way that she distributed, right, her mass right now, the arms extended, moment of inertia is actually large. And let's say she's spinning here with some omega initial. Let me do it like this with omega initial. Next, what she can do here is she can, draw her arms closer together like this. So then her moment of inertia final is less than moment of inertia initial. But there is very little net torque, right? So the net torque can be eliminated. That means then L initial has to be L final. So if I have I initial, omega initial, this should be equal to then omega final times I final. But I'm saying that omega final is not equal to the initial, sorry, moment of inertia final is not equal to the moment of inertia initial, because she changes her shape, and she changes her shape, she's decreasing her moment of inertia, which means now for these products to be equal to one another, then so that means we are basically decreasing I final. So then omega final has to increase to compensate, and what we have, she starts spinning with a much greater angular velocity, right? So let me show you that in a nice little video. All right, so here you can see how angular, let's say this is the original shape like this, and this is her speed, and then as she decreases her moment of inertia, see by how much her angular velocity increases. So this is the conservation of angular momentum. Perfect example of that. All right, so you can see again, angular velocity starts increasing as she changes her or decreases her moment of inertia. All right. All right, so that's basically what we have. So to conserve the angular momentum, her angular speed must increase then. All right, so the same thing then can be used in, similar examples. So here we have a small mass M attached to the end of a string, revolves in a circle on a frictionless tabletop. The other end of the string passes through a hole in the table. Initially, the mass revolves with the speed V1 equals 2.4 meter per second in a circle of radius R1, which is 8.8 meters. The string is then pulled slowly through the hole so that the radius is reduced to R2 equals 0.48 meters. What is the speed V2 of the mass now? All right. So we pretty much, what we can say here is, because there is a frictionless tabletop, so I can say angular momentum before and after is exactly the same. Or let's say 1 and 2 like that. L1 equals L2. Since it's a particle, I can say that M1 R1 V1 equals M2 R2 V2. But since it's the same object, I can just pretty much cancel the mass from both sides. So it becomes R1 V1 equals R2 V2. And I can just solve for the V2, which is this is then R1 over R2 times V1. So this is then 0.8 meters over 0.48 meters, then times 2.4 meters per second. So let's cancel out. Then we get V2 as 4 meters per second. We could see, right, because we are getting closer, right? So that means we're decreasing the radius, so then the speed has to increase, right? So if the R2 decreases, V2 has to increase in order to compensate. So the small mass starts spinning faster, right? As we get closer to the, to the pivot point. All right, so here's another example, which is basically takes into account two discs, let's say, right? Two cylindrical plates. So a simple clutch consists of two cylindrical plates that can be pressed together to connect two sections of an axle as needed in piece of machinery. The two plates have masses MA equals 6 kilogram and MB equals 9 kilogram with an equal radii, which is 0.6 meters. They are initially separated. Plate MA is accelerated from rest to an angular velocity omega 1 equals 7.2 radians per second in time delta t equals 2 seconds. So for part A, we want to calculate what is the angular momentum of the mass A. Okay, basically the plate A, angular momentum of plate A. All right, so let's do that. So to calculate that, so we need to then say, all right, so here's part A. So angular momentum of A is equal to then moment of inertia times angular velocity. So moment of inertia is basically 1/2 mr square, and then angular velocity. So basically put like angular velocity like that. So then I can write it down as 1/2. Mass was 6 kilograms. Radius was 0.6 meters square, then times 7.2 radians per second. So this is equals to 7.8 units of angular momentum, kilograms, meter square per second. That's the units for the angular momentum. So that's my angular momentum of that disk A, the instant, right, of t equals 2 seconds. As you can see, right, because it is accelerating, a little bit later, its angular velocity is higher, so its angular momentum can actually change. But this is at that instant of time. Now, after that, for part B, it says, what is the torque required to have accelerated MA from rest to omega 1? Okay, that means we want to find the torque. So there are two ways I can do that, honestly. First, I can find um, angular acceleration. So technically, I can say omega 0, so sorry, omega 1 equals omega 0 plus alpha times t, and I can solve for alpha, and I can use the torque is equals to I times alpha. I can do that using the Newtonian, the dynamics, right? Rotational dynamics. But we now know a different way. I can say then change in angular momentum as a function of time is then, my torque, net torque, which means then I went from, L1 minus L0, right, divided by delta t. So initially, when it was just at rest, it had no angular momentum, but now its angular momentum is 7.8 kilogram meter square per second minus 0 in a time of 2 seconds, right? Then this will give me 3.9 newtons times meters. You can see, right? It's easier in one step rather than, in two steps over there, which is still something we could do, possible. The next one says, next, plate MB is initially at rest, but free to rotate without friction, is placed in firm contact with freely rotating plate MA, and the two plates both rotate at a constant angular velocity omega 2, which is considerably less than omega 1. Why does this happen, and what is omega 2? Well, in a way, you can think like, let's say this is kind of like very similar to the um, collision, right? So let's say perfectly inelastic collision when two things, let's say put together, right, or collide together and they stick together afterwards, because we are told that they have same angular velocity afterward, they rotating together. That means what we can do here is this. This is part C, right? For the system, L initial or L1 is equals to L2. So this is then for in terms of my system is L1 initial plus L, well, thing like this. So since MB was initially at rest, it didn't have angular momentum. So the angular momentum of my system before it was just the angular momentum of the particle A, right? So I can say LA1 plus LB1 equals then L of the system, at later times too, right? So, but this is 0 because particle MB, right, or the plate MB was initially at rest, so it didn't have any angular momentum the instant when they collided. So then this is basically L2, which is the final angular momentum, is equal to the initial angular momentum of the, plate A, right, before that, which means this L2 is equals to 7.8 kilogram meter square per second. But then L2 is equals to uh, angular momentum of the two plates combined together, which means this is equals to I of A plus I of B times omega final, which means omega final or omega 2, right? So not omega final, omega 2, because we're using 1 and 2. So then omega 2 is equals to then angular momentum 2 divided by moment of inertia of, that means this is 1/2 MA r, well, they have the same radius, right? R square plus 1/2 MB r square. And since I have L2 and I have their mass, MA and MB and radius, I can just plug in there and calculate. So then omega 2 will be 2.9 radians per second. So we can calculate from there. All right, guys. So this concludes this chapter.